Example number 3, an initial investment of $50,000 earns 4.5% compounded continuously. Also, $5,400 is withdrawn each year. Can we find the amount at any time t? Okay, so just recognizing right which application you need. So obviously they mentioned about compounding continuously, but in addition to that, we're taking money out each year, and this is a lot more realistic for how investments work. We're withdrawing $5,400, so it's earning interest, so it's going up, but then we're also taking out, and we're going to take out more than the interest that it earns, and eventually this account is going to make its way down to zero. Is the idea. So we're going to kind of use all of our money over time, but still gain interest along the way. What is that? That's an annuity. Okay, really good way to plan for retirement and that sort of thing. Okay, so we're going to use the annuity with continuously compounded interest formula to start off here. This was the general form. dA over dt equals RA minus M. So it's still the continuously compounded interest, but now we subtract M is the amount of money that we withdraw. Usually though, we don't want to think of it this way. We want to think of it, oh, my mistake. It's getting a bit ahead of myself. So let's plug those values in. There's our interest rate. There's the amount we withdraw. But we want to write this in the form of a linear differential equation. We want to move this term to the other side, like so. Let's do that. Okay, now it looks like, a prime plus f of t a equals g of t or something like that, right? That linear form where we've got the derivative of a plus something times a equals something else. Okay. Again, here it's pretty simple, right? This function, just a constant. This is just a constant. It's a matter of setting it up. That's the hard part. And then of course, for these, you always have your initial condition. Here we know that the original amount in the account, the amount at time zero is 50,000. How do I even start to set up my initial condition, you might ask? We've done a few of them, but maybe that's still not quite clear. It's always going to be your function a, right, that appears here and here, or maybe it's y, right, of some time, because you're taking the derivative with respect to t. It's a of t. So the amount, since a is the amount in the account, the amount at time zero equals 50,000. That's the information that we know. All right, once we've got it all set up, now it's a matter of solving this differential equation. And we're going to do that in the linear equation style. So if you recall, first thing we need to do is look at what we've got here in front of a, find the integrating factor. It's all by the linear method. Okay. Oh, here we are. The integrating factor, it's e raised to the integral. Don't forget that negative 0.045 dt. Again, a very simple integral, so long as you know what you're looking for. E to the negative 0.045 t. And do you know what to do next? We take our integrating factor and multiply it to all three. And it looks monstrous for a moment, but that left side is going to simplify really well. So there we've got our integrating factor there. We've got it in between here, and we've got it over here. Trying to slide my pages up. They're kind of sticking. Now, what happens to that left side? What's my big bracket there, if you recall from 9.3. Every time, as soon as you multiply that to the left, this is the product rule, the result of a product rule. It's your integrating factor times your variable, or your function, I guess you would say, a. So I've got my integrating factor, the derivative with respect to t, integrating factor times a. And I'm just going to copy this part. Now we really like this because if I now integrate over here, I'm going to cancel that out. So I integrate both sides with respect to t. And the derivative there is gone now, but I do need to take this integral. Luckily though, as integrals go, this one, pretty simple. You could use a u sub there, u being your exponent on e, or if you can kind of see how it works. Oh, looks like I'm done with this page. Here's your antiderivative. So I'm just dividing by my what would be my chain rule up there, right? Still just copying the left side. Now doing the antiderivative plus c. Once we clean that up, that division actually turns out really, really well. E to the negative e to the negative 0.045t times a equals 120,000 e to the negative 0.045t plus c. And whenever we solve with a linear differential equation, it's always really easy to get the explicit solution. We're going to divide by this. And when we do, it's going to cancel this one, but don't forget about the c. There you go. So when we divide both sides by our e, right, cancels out there. When I divide here, if it goes underneath, but it's a negative exponent, I can then move it to the top and turn it into a positive exponent like so. Which is really helpful for the next step. At this point, we have our explicit solution. Now we're going to apply our initial condition. And, certainly this is our third example, and you can tell, all these problems are quite long. But if you're methodically going through the steps, and once you get really familiar with the solving techniques, which maybe you even are at this point after doing homework, then these go pretty quickly. It's just a matter of pounding it all out. Okay, so once we've got our explicit solution, apply, got your value of t, got your value of a, we're going to solve for c. Now we really like that 0 here because all this just becomes 1. And if we subtract pretty quick, we get c to be negative 70,000. All right, we're going to take that c. I know I'm going really fast. We're going to plug it in right there. And that is the answer to part A. This is the amount of the annuity at any time t. And so if you explore this a little bit, right, what is the amount at time 0? If t equals 0, wouldn't this whole thing be 1? And we'd have 120,000 minus 70,000. That's the 50,000 that we started with. But as t starts to get bigger, then we're subtracting something more than 70,000, and it's, the value is getting less and less and less. So it's actually, a pretty simple equation, but who would have thought it was that, right? You've got your interest rate, you got your e for the exponent. It's like an exponential decay. Okay, anyway, fascinating. So simple too. Okay, there's a follow-up part to this. This would probably be really good to know for whoever's annuity this is. After how many years will the amount in the account be zero? How many years can they withdraw this $5,400 before it's gone? There's no money left. So you think, well, mathematically, what does that mean? We need to solve this. At what time will the amount be zero, right? And we'll use, obviously, our solution here. So we're going to plug in 0 for the amount, find out how long it takes. We'll definitely want to know before we even start withdrawing how long we got, right? Okay, so setting it equal to 0, solving for t actually goes pretty fast. If we add our 70,000 e to the 0.045t onto the left, and then, we can divide by the 70,000, reducing to 12 over 7. All right. Take a natural log of both sides to cancel out the e. Finally, divide by that decimal. And there it is. 11.98 years when I round to 2 decimal places. So we got really 12 years that we can take out that $5,400. I think in that final year, in that 12th year, we'll probably end up with a little bit less because it was a little bit short. But we pretty much got 12 full years, which I don't know. Maybe 12 years is fine. Maybe 12 years is not that long, and we should make other plans. Anyway, this is example of that third application. See you in the next video.